Hi class. This video covers section 4.5, where we'll continue to talk about the method of undetermined coefficients and introduce what's called the superposition principle. So we are continuing to look at equations that are second order, linear, constant coefficients, and we're still looking at the non-homogeneous case where we have this non-zero right-hand side. And in the last section, we looked at the case where this function just has one term. It's just like e to the t or sine of t or t squared, something like that. And when we did this, when it's one term, we covered this in section 4.4. And we used this method of undetermined coefficients where we took a guess at what the solution would be and then figured out what the details of that guess would have to be. And so one term is pretty restrictive, so now we're going to consider the case where we have multiple terms. And that's this section. When you have multiple terms, it's actually pretty straightforward generalization to use the method that we learned in the last section for multiple terms, and that's what's called the superposition principle. So I will write it out right now. So here it is. The situation that we are in is that we've got our, our standard kind of equation that we're used to. And on the right-hand side, our non-homogeneity has multiple terms. So it's got something and maybe multiplied by some constants. And we're assuming the if part is that we know a solution to the same left-hand side with just this single term here. And note that the theorem doesn't say that this has to be a single term. It's just some function, which we know how to find a solution for. And so we're going to apply this to the case where we have, we know how to find the solution where we have a single term on the right-hand side. And so if you know a solution to the equation with this particular term on the right-hand side, and then you know the solution y2 to the same equation, except on the right-hand side, we now have a different term, then you can, so if you have those solutions, y1 and y2, you can find a solution to some linear combination of those terms, of those right-hand sides over here. And all you do is take the same linear combination of the known solutions, okay? So if you change your right-hand side to kf1 plus kf2, then your solution to that is going to be k1 y1 plus k2 y2, okay? And the proof of this is super straightforward. Let's do it. So we need to show that this is a solution to this equation here. So we'll just plug it in, right? So we'll take a times k1 y1 plus k2 y2 double prime plus b k1 y1 plus k2 y2 prime plus c k1 y1 plus k2 y2. Okay, we need all of this stuff ultimately to equal the right-hand side over here. And so what this proof hinges on, and we've seen this kind of play out before, this hinges on the fact that this derivative operator, when we do this, it's going to respect the linearity of what's inside the parentheses. So if we have to take the second derivative of the stuff in the parentheses because of, the linearity of the derivative, we can just put those derivatives onto the y's. So then we get a times k1 y1 double prime plus k2 y2 double prime. That's the gist of this. That's why this works. oops. So let me correct this here. That is not supposed to be there. That was a 1. There we go. Okay. Sorry about that. And so then we get 1 prime plus k2 y2 prime plus c k1 y1 plus k2 y2. And so now we can split this out into like basically a left-hand side for each of the y's. So we can pull the k1 out and we get a y1 double prime plus b y1 prime plus c y1. So those are all the k1 terms, and then we get a k2, and then the same thing but with y2. So a y2 double prime plus b y2 prime plus c y2. And because y1 is a solution to this equation, the y1 plugs into the left-hand side equals f1. So this is f1, and this is f2. So all of this stuff equals k1 f1 of t plus k2 f2 of t. And that's it. That's what we wanted. I don't really feel like doing an example of this because it's kind of boring, but I will point you to an example of the book. Example in the book. See example 1 on page 181. If it doesn't really like, if this just looks like a lot of letters and it's not really sinking in what this means, and we'll see more examples of it. I'll do an example of it in the discussion and everything like that. But really, I want to get to the bigger sort of principle of finding these solutions to the non-homogeneous equations. Because what we've done so far in sections 4.5 or 4.4 and up until right now is we've been looking for a particular solution. So remember, and I've talked about this before, but remember that a particular solution, as the name implies, is one particular solution to the ODE. But what's much more general and much more desirable is a general solution, which characterizes all of the solutions to the ODE. So we found in the homogeneous case that we learned how to find a general solution. And that's what I've written down right here. So in the homogeneous case where the right-hand side f of t equals 0, we learned that if you've got y1 and y2, which are two linearly independent particular solutions. So if you can find two particular solutions and they're linearly independent, then you get the general solution, which is this family of functions parameterized by these two constants, C1 and C2. And that describes any possible solution to your ODE. And so that gave us the theorem to where if we were given an initial value problem and we got our two, our initial position and our initial velocity, or our initial y and our initial y prime, then we could solve for those constants and we could get the solution to the initial value problem. Any solution to the ODE has this form. So that's what we want in our non-homogeneous case. And that's what we're going to talk about right now. Just like in the homogeneous case, we had these like 2 degrees of freedom, right? Which made sense because we have a second order equation. In our first order equations, we usually only had one constant, and in our second order, we have two. So we'll expect that even in the non-homogeneous case, that we'll sort of need these two constants also. So let's think about our equation again. Let's write it out. We get ay double prime plus by prime plus cy equals f of t. So I'm going to write this instead. I'm going to write the right-hand side as 0 plus 0 plus f of t. So so remember from the superposition principle that we just learned, if we want to find a solution to this, we can sort of take each term on the right-hand side separately. So we can take this equation, and let's say we have a solution to this, y1. And now let's take, let's try to draw this one, which is, of course, the same one. So these are both the homogeneous equation, but let's say we have a solution y2. So these are both the, so like green and yellow are the homogeneous equations. And then let's say we have our third one here, which is this one. So the red is non-homogeneous equation. And let's say that we have a particular solution to this, and I'm going to call this yp for particular, and that's going to be clear in a second. And then I'm going to do one more crazy thing, and I'm going to just put a C1 here and a C2 here, because of course this is still my same equation because I'm just multiplying these constants by 0. So by our superposition principle, we get that C1 y1 plus C2 y2 plus yp is a solution to that equation up there, okay? Because we expanded out our right-hand side, and the y1 and y2 part is like the exact statement of the superposition principle, and then really the yp part is also. So if we have a solution y1 and y2 that are solutions to the homogeneous equation where that f is equal to 0, and then we add up all of those right-hand sides with our constants and everything, then we get that the same combination of the solutions is a solution to the equation where the right-hand side is that combination, okay? So this thing here is a solution to the equation that we are concerned about, and it's got these 2 degrees of freedom. So this looks like a general solution. It looks like you might be able to pick constants that give you the right things to find the solution to any initial value problem. And so it seems like a reasonable guess for our general solution. And in fact, it is the correct guess for our general solution. So I will write this down in the theorem. Although I'll say first that it looks like a general solution if y1 and y2 are linearly independent, just like we had in the homogeneous case. Okay, so that's going to go in the statement of the theorem. So here's our statement. For any numbers which are going to go ahead and these are going to define an initial value problem. Okay, so that's what we're essentially saying. We're talking about an initial value problem where you've got your A, B, and C and your f of t picked and your initial conditions at some t naught. So your y at t naught equals y naught, and your y prime at t naught equals y 2. Why did I say 2? That should be a 1. Sorry. That's a 1. So if you have an initial value problem, then the way that you find a solution is by considering first the equation, the non-homogeneous equation. So that's what NH stands for. And so suppose that you have a particular solution to the non-homogeneous one. And that next you consider the homogeneous equation where you set the right-hand side equal to 0. And let's say that you can find two linearly independent solutions to that. Okay, and we know how to do that in every case because you just solve the characteristic equation, blah, 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 blah. Then this theorem says if you have solutions to, if you have those three solutions, yp, y1, and y2, then there exists a unique solution to your initial value problem. Not only do you get existence and uniqueness, but it tells you exactly how to find it. It's given by this formulation right here, where you have some y1 plus y2 times constants, so some constants, plus your particular solution, which doesn't have a constant by it. Okay, so this tells you this is how you solve initial value problems when the right-hand side equals 0. And I'm gonna pretty much skip the proof. I will say that the proof is very, very similar to the existence proof that we saw in section 4.2 for the homogeneous case. It's easy enough to see that, in fact, we just discussed this, that this is a solution to NH. And so what we really need to prove is that you're always going to be able to find C1 and C2 that solve the initial value problem. And that's really just an algebra problem. So you can plug this in and to the IVP, set everything equal to y0 and y1, and do the algebra out. And so then the only trick is that you have to make sure that the solution that you get is always going to exist. And what you end up with is the term in the denominator that looks like y1 at t naught times y2 of t naught minus y1 prime of t naught times y2 of t naught. And you need that to be non-zero. And that is the case if y1 and y2 are linearly independent. So we saw that, we went through and proved that statement in section 4.2, and that was the key to that proof. And it's the same key to this proof here. So that's pretty much all I'm going to say. You can go and look in the details in the book if you like. So now I'm going to make one more comment to connect this to what we've seen before. So remember, we learned how to solve linear first order equations that looked like this. And just a y prime plus some function of x, p of x, y equals some q of x on the right-hand side. And if q of x equaled 0, so that would be our like homogeneous case, then the equation is separable, and you can see that the solution is going to look like this. Y equals c times e to the negative integral of p of x, which you can just sort of move the x's to one side and blah, blah, blah. Now, if q of x is not equal 0 in the non-homogeneous case, we define an integrating factor and we let mu of x be e to the integral of p of x. And the solution is y equals 1 over mu of x integral mu of x cubic plus a constant over mu of x. So you can sort of go back to when we learned about uh, the solutions of this, which is a good thing to review anyway in advance of the midterm, and remember that this is what this looked like. So note that this thing is exactly this right here, because we have the negative sign there. So in other words, this is the general solution to the homogeneous equation. And it's general because we've got that C there that we can vary depending on what our initial conditions there. And if C was equal to 0, this term would go away, and this term here would still be a solution to the non-homogeneous. So this term by itself is not a general solution. You need to have this to be a general solution to the non-homogeneous one. But this is a particular solution to the non-homogeneous equation. And then if you put them together, if you put a general solution to the homogeneous, call that H, and plus a particular solution to the non-homogeneous, then that gives you the left-hand side, or the whole thing together, is the general solution to the non-homogeneous equation. So it's the same form that we see now in the second case, where in order to get general to non-homogeneous, you need a particular to non-homogeneous plus the general of the homogeneous. And so that's the connection here. So in summary, basically what we've learned is how to use undetermined coefficients for a broad variety of non-homogeneities of right-hand sides. And so I showed a table in the last video, and I'm going to show a sort of updated table now. So this table is on page 184 in the book. And again, this looks a little bit different because I've pulled it from an older edition of the book, but it says the exact same thing. And so this is really the same thing that we had in the last section, except it applies to multiple terms, where the multiple terms are sort of expressed in terms of these polynomials here. So this is multiple terms. And you can always break apart the equation so that they each look like this, where you have some polynomial with an e to the t, or a polynomial with a cosine or a sine. So what you can do if you have, ay double prime plus by prime plus cy equals, f1 of t plus f2 of t, and the garbage trucks are here today. That's what you're hearing in the background. So if you've got two that kind of put together don't look like one of these forms, then just, find y1 that solves this one, and then find, oops, is it wrong? Y2 that solves this one, and then put them together, y1 plus y2. So you just break it apart. So I'm not going to, I'll do some examples in class. I'm not going to do a bunch of examples here. But I'll say see examples in the book, and then do lots of practice in the homework. And that's why I think in this homework set, I say, hey, you can do extra problems if you want more practice, which seems like, why would you want to do that? But the answer is, if you're not getting it, just doing more and more examples will help you out. All right, that's it for this section. Thanks a lot.